So welcome back. So the question is are there two functions which are harmonic and they are not harmonic conjugates at the same time? So the question is, are there functions which are harmonic but not conjugate harmonic? So that's the question. So let's try to answer from this example. So let u to be the function x squared minus y squared, and v to be the function y x squared plus y squared. Are both u and v harmonic? Are they conjugate harmonic? So we'll try to get the answer to this question by working out through this problem. So let's start with u. So u is x squared minus y squared. So which means partial u partial x is 2x. Partial squared u partial x squared is 2. Partial u partial y is minus 2y. And partial squared u partial y squared is minus 2. So this implies that partial squared u partial x squared plus partial squared u partial y squared is 2 plus minus 2, which is 0. That is, u is harmonic. So the function u is harmonic. Next, v is given by y over x squared plus y squared. So partial v partial x partial v partial x so this v partial x. So these are quotients, so we just use quotient rule. So I have u prime v minus v prime u over v squared. So differentiating this with respect to y, we get 1. So times x squared plus y squared minus v prime, we get 2y times u, which is y, x squared plus y squared squared. This is the definition of partial v partial y, not partial v partial x. So partial y. So which will be x squared plus y squared minus 2y squared over x squared plus y squared square. So this will give me x squared minus y squared over x squared plus y squared square. So which tells me that partial squared v partial y squared. So we use quotient rule. So v u, and then this one v. So u prime, this with respect to y will be minus 2y into x power 4 plus 2x squared y squared plus y power 4. I'm simply expanding the v minus v prime. So v prime, the first thing I'll have to draw. In fact, there's no need for me to expand this. There's no need for me to expand the v. So once I have my u prime, which is minus 2y, v is x squared plus y squared square, minus v prime, derivative of this one will give me 2. I drop 2, differentiating inside, I get 2y, and then power reduces by 1. And so I multiply by u, which is x squared minus y squared. And then over x squared plus y squared power 4 now. So this will give me, so this is common. X squared plus y squared is common to this and this term. So I put brackets minus 2y into 1 of the x squared plus y squared minus 4y into x squared minus y squared. Divided by x squared plus y squared power 4. Which you can now simplify. This and this, one of them will cancel, so that we have minus 2x squared y minus 2y power 3 minus 4y x squared plus 4y power 3 divided by, so 1 will go x squared plus y squared, so then power 3, because this one cancels with one of the powers. So this is my partial squared v partial y squared, which can be reduced to, so this y cubed and this y cubed will give me 2y cubed, and then minus, this will give me 6 x squared y, x squared plus y squared power 3. And then let me call this one number 3 for my labeling. I can just call it even 1, so there's no labeling in this case here. Let me label this 1. And then next one. So we have to get, remember V is given by y over x squared plus y squared. So if I let this one to be my u, this one to be my v, so u prime v minus v prime u over v squared then, and remember I have partial one partial v partial x. So u prime is 0, so I'll have 0 times v minus v prime, I get 2x times u is y. So this is what I get. So which will give me minus 2xy divided by x squared plus y squared squared. So that's my, let me call this one 2. So to get partial squared v partial x squared, I differentiate partially this with respect to x t. So as usual, there's this by u, this over v. So u prime is minus 2y times v, which is x squared plus y squared squared minus v prime. So I'll have to write 2, and then differentiating inside I have 2x, and then the power reduces by 1, and then I multiply by u, which is minus 2x y, and then x squared plus y squared. When you raise to power 2, this, or the square of v, you get 4. This equals to, now x squared plus y squared is common, this part and this part, so I factor it out, x squared plus y squared into, so denominator is x squared plus y squared power 4. First will be minus 2y into x squared plus y squared. This other one will be now minus will be plus. 2 by 2 by this will be 8. So 8x squared y. And then I close this. So which will give me partial squared v partial x squared. Now this bracket and this bracket are the same. So this cancels 1. So I have x squared plus y squared power 3. Now this will be minus 2x squared y minus is still minus. So I have minus 2y power 3 and then plus 8x squared y, which is x power 3, x power 2 plus y squared power 3. Now 8x squared y minus 2x squared y gives us positive 6x squared y, and then minus 2y power 3. So call this one number 3. So 1 is partial squared. So equation 1 plus equation 3 implies that we have partial squared v partial x squared plus partial squared v So plus 3 will be partial squared v partial x squared plus partial squared v partial y squared equals to, so this one LCM is x squared plus, the denominator is this 6x squared y minus 2y cubed plus the other one, denominator is the same, but numerator is 2y cubed. 2y cubed minus 6x squared y divided by x squared plus y squared over 3. So that partial squared v partial x squared plus partial squared v partial y squared, LCM of these numbers, these two fractions is x squared plus y squared over 3. So 6x squared y minus 2y cubed plus 2y cubed minus 6x squared y. I hope this is very direct to see that the numerator is going to be 0, because going to be 6x squared y minus 6x squared y minus 2y squared y cubed plus 2y cubed divided by x squared plus y squared over 3. So that these two give 0, these two also gives 0. So you have 0 divided by x squared plus y squared power 3, and that is 0. So since the sum of these two second order partial derivatives, since partial squared v partial x squared plus partial squared v partial y squared equals to 0, then v is also harmonic. V is harmonic. But we have not yet finished. So two functions u and v are now harmonic. Let's see whether they are conjugate harmonic. So note u and v are conjugate harmonic if and only if they satisfy the CRE, IE, partial u, partial x equals to partial v, partial y, and partial u, partial y equals to minus partial v, partial x. Now from our calculation, partial u, partial x, remember u is given by 2 by x squared minus y squared. So partial u, partial x is 2x, partial v, partial y. So remember v is given by y over x squared plus y squared. So u v, u prime v minus v prime u over v squared. So u prime is 1 times v x squared plus y squared minus v prime is 2y into u x squared plus y squared square. So this will give you x squared plus y squared minus 2y squared over x squared plus y squared square. When you simplify partial v, partial y, you get x squared minus y squared over x squared plus y squared squared. But this is not the same as partial u, partial x, which was giving us 2x. So this first equation is not satisfied. So once you can see that any of the two equations is not satisfied, then you conclude that two functions are not harmonic. Conjugate harmonic, not harmonic. So since the first CRE equation is not satisfied, and even the second, then U and V in this problem are not conjugate harmonic. Conjugate harmonic. From this calculation, then we can see that. So therefore, there's a possibility. So the question to the answer to our question is hence it is possible to have two functions which are harmonic but not necessarily harmonic conjugate. So there's a possibility of that one. So when you say two functions are harmonic, does not necessarily mean that they are harmonic conjugates. So for you to show that they are harmonic conjugates, you have to show that they also satisfy all the two Cauchy-Riemann equations. Thank you.